In 2012, 4 physicists published a paper that threatened to destroy everything I'd spent 20 years building. They claimed that black hole horizons, those invisible boundaries around black holes, must be walls of infinite energy. Firewalls that would incinerate anything trying to cross them. If they were right, my theory of black hole complementarity was dead. Quantum mechanics, as we know it, might be broken. I was on sabbatical, walking on a beach in Northern California, trying to clear my head. And that's when it hit me. Einstein and Rosen wrote about wormholes in 1935. Einstein, Podolsky, and Rosen wrote about quantum entanglement, Tichy Sam Yayar. What if they weren't describing 2 different things? What if wormholes and entanglement are the SAM phenomenon? I called Juan Maldacena immediately. I said, Juan, ER equals EPR, wormholes, AR entanglement. There was a long pause. Then he said, holy shit, Lenny, write it up. Let me tell you that story. So it's 2012. I'm 72 years old. I've been working on the black hole information problem for almost 30 years. I thought I'd solved it back in 1993 with black hole complementarity. This idea that an observer falling into a black hole and an observer staying outside can both have valid descriptions of what happens, and they never contradict each other because no single observer sees both perspectives. It was beautiful. It preserved quantum mechanics. It explained how information could survive black hole evaporation without creating paradoxes. And for almost 20 years, it held up. Then in July 2012, I get an email from a colleague. Lenny, you need to see this. It's a preprint, a paper by Ahmed Al-Mary, Don Merolf, Joe Polchinski, and James Sully. They called it the AMPS paper after their initials. And it was a direct attack on complementarity. Their argument was elegant and brutal. They showed that if you believe in 3 things, the one, that Hawking radiation is in a pure quantum state, two, that information isn't lost, and else 3, that there's nothing special at the horizon when you cross it, then you run into a contradiction. You can't have all 3. Something has to give. And their conclusion, the horizon must be a firewall, a place where the vacuum energy goes crazy and creates infinite temperatures. Anyone or anything crossing it gets instantly incinerated. I remember sitting in my Stanford office reading this paper and thinking, this can't be right. Joe Polchinski, one of the smartest people in string theory, was claiming my complementarity principle was wrong. But his argument was tight, really tight. I spent weeks trying to find the flaw. I couldn't. The logic seemed bulletproof. But at K&W, it had to be wrong. Black holes can't have firewalls at the horizon. That would violate everything we know about general relativity. If you're in free fall crossing a horizon, you shouldn't feel anything special. That's the equivalence principle, the foundation of Einstein's theory. So I did what I always do when I'm stuck on a problem. I went on sabbatical. Got away from Stanford, away from my office, away from the pressure. I rented a place in Northern California, right on the coast, and I walked. Every morning, I'd walk along the beach, just thinking, let me back up and explain what the firewall problem actually is. Because it's one of those things that sounds simple but gets really, really deep really fast. Here's the setup. You've got a black hole. It forms, it sits there, and it slowly evaporates through Hawking radiation. Now, Hawking had shown back in the 1970s that this radiation is thermal. It's just heat, random noise. No information comes out. But I'd spent 20 years arguing that this can't be the whole story. Information can be destroyed. Quantum mechanics forbids it. So the radiation has to loc thermal, but it must actually be encoding all the information about what fell into the black hole. It's scrambled, incredibly scrambled, but it's there. The problem is entanglement. Let me explain. When Hawking radiation comes out, each photon or particle that escapes is entangled with something that fell into the black hole in the past. Think of it like this. You create a pair of quantum particles, twins, perfectly correlated. One escapes as Hawking radiation, the other stays inside. They're entangled. That's standard quantum mechanics. But here's where it gets weird. If you want the information to eventually come out, if you want the radiation to carry information about what fell in, then the radiation also has to be entangled with ALL, the EVOS radiation that already escaped. Otherwise, there's no way to reconstruct what fell in. The information would be stuck inside forever. So now you've got a problem. Each particle of Hawking radiation near the horizon is entangled with something inside the black hole. But it's also entangled with radiation that already escaped. And quantum mechanics says you can't do that. A quantum system can't be maximally entangled with 2 different things at once. It's called the monogamy of entanglement. If you're married to one system, you can't also be married to another. You have to pick. This is what AMPS figured out. They said, if you force the radiation to be entangled with the earlier radiation, which you need for information to escape, then it can't also be entangled with stuff inside, which means the smooth quantum vacuum at the horizon breaks down. The entanglement structure that creates empty space, gone. And what you get instead is a firewall. When I first saw their argument, I thought, okay, maybe for really oldie black holes that have evaporated more than half their mass, maybe Teishin, you get firewalls. But the AMPS paper was claiming firewalls exist even for Young black holes that just formed. That can't be right. Because think about what that means. If I'm standing far away from a collapsing star, watching it form a black hole, I should see a perfectly smooth horizon form. Nothing special happens there in my description. But if I'm falling in, according to AMPS, I hit a firewall and get vaporized. That's a disaster for general relativity. It's saying that observers at rest and observers in free fall see fundamentally different physics. That violates the equivalence principle, the core of Einstein's theory, so I knew AMPS had to be wrong. But I couldn't figure out how they were wrong, so I'm walking on this beach. It's early morning, probably 6 a.m. The fog is just starting to lift. And I'm thinking about entanglement. Entanglement is this weird quantum thing where two particles are connected in a way that seems to violate everything we know about space. You measure one particle here, and instantly, faster than light. You know what you'll get if you measure the other particle, even if it's on the other side of the universe. Einstein called it spooky action at a distance. He hated it. But here's what I was thinking about that morning. What is entanglement, really? What's the physical mechanism? In quantum field theory, we describe it mathematically. Two particles share a wave function. They're in a superposition, all the standard stuff. But that's just math. What's actually happening? And then I remembered something. Back in 1935, the same year Einstein, Podolsky, and Rosen wrote their famous EPR paper about entanglement, Einstein and Rosen wrote Anotar paper about wormholes. They showed that you could have a solution to Einstein's equations where space is connected through a bridge, a shortcut through space-time. They called it an Einstein-Rosen bridge. We call them wormholes today. Two black holes connected by a tunnel. I stopped walking. I just stood there on the beach, staring at the ocean. What if these aren't two different things? What if Einstein and Rosen were describing the same phenomenon twice, using two different languages? Here's the idea. When two particles are entangled, they're connected by a wormhole. A tiny, non-traversable wormhole. You can't send signals through it, you can't travel through it, but it's there. The geometry of space is different because of the entanglement. The particles are light or alloy connected through the fabric of space-time. ER equals EPR, Einstein, Rosen bridges, Podolsky, Rosen entanglement. I literally ran back to the house. I called Joan Maldacena. Joan is at the Institute for Advanced Study in Princeton, probably the smartest person I know. If this idea was crazy, he'd tell me. The phone rang, Joan picked up. I said, Jean, I think I've figured out the firewall problem. ER equals EPR. Wormholes are entanglement. Long pause. Then, holy shit, Lenny, that's beautiful. Write it up. Now, so here's how it solves the firewall problem. Remember AMPS said that Hawking radiation can't be entangled with both the interior of the black hole and the previously emitted radiation. Monogamy of entanglement. You can't have both. But what if you can have both because they're connected by wormholes? Think about it. Early Hawking radiation escapes. It's entangled with stuff inside the black hole, connected by tiny wormholes. Later radiation also escapes. It's also connected to the interior by wormholes. But now all that early radiation has built up this huge network of wormholes connecting it to the black hole interior. When NEW radiation comes out, it's entangled with the old radiation, THROGH, those wormholes. The wormhole network grows. It's like a web connecting everything. The radiation isn't violating monogamy. It's building geometry. And here's the key, this geometry. These wormholes, they keep the horizon smooth. No firewall. The equivalence principle is save. An infalling observer doesn't see anything special at the horizon because the entanglement structure is still there, just in the form of wormhole geometry. Joan and I started working out the details. We'd email back and forth, have phone calls, work through the math. This wasn't me fighting someone. This was two physicists excited about a crazy idea that might actually be true. The more we worked on it, the more beautiful it became, because it wasn't just about black holes, it was about the nature of space itself. See, in quantum field theory, empty space, the vacuum, is full of entanglement. Virtual particles popping in and out of existence, creating this web of quantum correlations. We always thought of this as abstract. But EPR says, no, this entanglement creates actual geometry. Space itself, the three-dimensional space you're sitting in right now, might be made of entanglement, woven together by these tiny quantum connections. Entanglement isn't something that happens in space. Entanglement series space, think about that. The two great revolutions of 20th century physics were general relativity, Einstein's geometric theory of gravity, and quantum mechanics, the probabilistic, weird, counterintuitive theory of particles and fields. For 100 years, we've been trying to unify them. We've been treating them as separate frameworks that we need to somehow merge. But EPR says they're not separate. Geometry is quantum mechanics. Spacetime is entanglement. They're two sides of the same coin, two languages describing the same reality. Einstein spent the last 30 years of his life trying to prove quantum mechanics was wrong. He wrote the EPR paper to show that entanglement was too weird, too spooky to be real. There had to be some underlying mechanism, some hidden variables that made it look like spooky action at a distance when really it was something local and sensible. And in the same year, he wrote about wormholes, geometric connections through space-time. He never saw the connection, but it was there the whole time. EPR, the mechanism he was looking for was geometry. Entanglement creates wormholes. Wormholes explain entanglement. When Joanne and I published Cool Horizons for Entangled Black Holes in 2013, the reaction was intense. Some people loved it immediately. They saw it as this beautiful unification of general relativity and quantum mechanics. Finally, a way to think about how geometry emerges from quantum information. Other people thought we'd lost our minds. Ed Witten, who's sharper than all of us, he was cautious. He said something like, it's a fascinating idea, but I want to see it work out in detail. Which is Ed's way of saying, I'm not sure this is right, but I'm not sure it's wrong either. Joe Polchinski, one of the Firewall paper authors, he was skeptical at first. We had a bunch of back and forth. He'd raise an objection, I'd respond, he'd raise another one. That's how physics works. You test ideas by trying to break them. But here's what was interesting, even the skeptics couldn't find a clear flaw. The idea was so simple, so elegant, that it was hard to dismiss. And it made predictions. It said that entangled black holes should be connected by wormholes, actual geometric connections in space-time. A few years later, in 2022, my colleague Adam Brown and I were part of a team that actually simulated wormhole dynamics in a quantum computer. We published it in Nature. We showed that you could create a system with two entangled quantum systems, and they'd evolve in a way that looked EXTLY, like sending a signal through a wormhole. EPR, tested in a lab. Now, to be clear, we didn't create an actual traversable wormhole that you could walk through. This was a tiny quantum system, a few dozen qubits, simulating the dynamics. But the point was, EPR makes testable predictions about how entangled systems behave, and those predictions were verified. The other big impact was on string theory and holography. See, Joanne had been one of the pioneers of ADS CFT. This idea that a gravitational theory in any de Sitter space is equivalent to a quantum field theory on the boundary. EPR fit perfectly into that framework. It explained though the boundary theory creates the bulk geometry, entanglement in the boundary theory creates wormholes in the bulk. My student Brian Swingle started working on this, showing how you could build up space-time from entanglement structure in the boundary theory. This became a whole field, tensor networks, quantum error correction codes, all this machinery showing how geometry emerges from quantum information. It's one of the most exciting developments in theoretical physics in the last decade, and it all came from that walk on the beach. Now, I have to be honest with you. EPR is still a conjecture. We don't have a complete proof. There are aspects of it that are murky, questions we haven't fully answered. Like, can you ever make these wormholes traversable? Can you actually send signals through them, or is the no signaling theorem absolute? There's also the question of what this means for quantum mechanics more broadly. If every entangled pair of particles is connected by a wormhole, then the universe is full of these connections. We're made of entangled particles. Does that mean there are wormholes running through your body right now? Probably. but they're tiny quantum scale, and you can't use them to teleport or anything fun like that. The firewall debate didn't end with ER-EPR. Some people still think firewalls might exist in certain situations. I wrote a follow-up paper in 2014 about computational complexity in black holes, arguing that creating a firewall would require an exponentially hard computation, essentially impossible for black holes formed by collapse, but maybe possible if you artificially trapped and manipulated the radiation. But the key point is ER-EPR gave us a way out. It showed that you don't NEE'd firewalls. There's a consistent picture where complementarity survives, quantum mechanics is preserved, and black holes are smooth at the horizon. So where does this go from here? What are we working on now? The big question is, can we make this precise? ER-EPR is a beautiful idea, but we need to turn it into rigorous mathematics. We need to understand exactly which entangled states correspond to which wormhole geometries. We need to know when the approximation breaks down, when quantum corrections become important. My group at Stanford has been working on this for the past decade. Adam Brown, Brian Swingle, Dan Roberts. These are the brilliant young physicists carrying this forward. We're using tools from quantum information theory, tensor networks, quantum error correction. We're trying to build a dictionary given an entangled quantum state. What's the corresponding geometry? There's also the question of de Sitter space, the kind of universe we actually live in. Most of the work on ER-EPR has been in anti-de Sitter space, which is a different kind of space-time. In de Sitter space, you have a cosmological horizon, a boundary beyond which you can't see, even in principle. How does ER-EPR work there? I've been working on de Sitter holography for the past 5 years, and honestly, it's harder than I thought it would be. The horizon in de Sitter space is observer-dependent. You and I have different horizons. How do you do holography when the boundary keeps changing? This connects to another thing I've been obsessed with: quantum complexity. Remember how I said creating a firewall would require an exponentially hard computation? That idea led to a whole research program about complexity in black holes. In 2016, Adam Brown and I conjectured that the quantum complexity of a black hole state is related to the volume of the wormhole connecting entangled black holes. Complexity grows even when entropy stops growing. It's like a new kind of thermodynamic variable. We called it complexity equals action. Black holes aren't just the densest objects in the universe, they're the fastest computers. They scramble information at the absolute physical limit. And the interior volume keeps growing as this scrambling happens, long after the horizon stabilizes. This connects back to ER-EPR because the wormhole growth is driven by entanglement complexity. The more scrambled the state gets, the longer the wormhole becomes. It's this beautiful connection between quantum information theory and general relativity. And then there's the Python's lunch problem. That's another paper Adam and I worked on with a few others. It's about why you can't actually decode Hawking radiation, even though the information is there in principle. There are geometric obstructions in space-time, regions where the complexity is so high that no observer could possibly extract the information, even if they had unlimited computational power. The information is there, but it's hidden behind what we call the Python's lunch, swallowed but not yet digested. All of this ties together. ER-EPR, complexity, scrambling, holography, they're all pieces of the same puzzle. We're trying to understand how quantum information and geometry are related at the deepest level. After 50 years of doing physics, I've learned something important. The best ideas often come when you're now sitting at your desk staring at equations. They come when you're walking, or taking a shower, or just letting your mind wander. That's what happened on that beach in Northern California. I wasn't trying to solve the firewall problem in that moment. I was just walking, thinking about entanglement, and my brain made a connection it hadn't made before. ER-EPR is one of those ideas that feels obvious in retrospect. Einstein wrote about wormholes and entanglement in the same year, 1935. For almost 80 years, nobody connected them. And then Juan and I did, and suddenly a whole bunch of problems started to make sense. That's the beauty of physics. The universe has these deep symmetries, these hidden connections, and sometimes you get lucky and stumble onto one. The math was there the whole time. Einstein had all the pieces. He just never put them together. I'm 86 years old now. I don't know how many more big ideas I've got left in me. But I'm still working on de Sitter holography, still trying to understand how our actual universe, with its accelerating expansion and cosmological horizon, fits into this holographic picture. It might be the problem that outlives me. But that's okay. Science is a relay race. You run your leg and then you pass the baton. And I'll tell you this, the idea that space itself is made of entanglement, that geometry emerges from quantum information, that's not going away. That's a fundamental insight about the nature of reality. Whether EREPR is exactly right, or whether it gets refined or replaced by something deeper, the core idea is here to stay. The universe is stranger than we imagined. And we've only just started to understand it. Next time, I'll tell you about the Python's lunch, why geometry itself conspires to hide information from us, even when it's technically there. It's another one of those ideas that hit me when I wasn't looking for it. But that's a story for another day.